Hello, everyone. It's a great pleasure and privilege to welcome you to the RIKEN Youth Talks. I am Xu Xiaoming from Tsinghua University, Shenzhen International Graduate School. So today, it's really a great pleasure to moderate our talks. And joining us today are distinguished young professionals who are leading the global research on organic electronics. So we are really privileged to have Professor Dion Khodagholy from Columbia University, Professor Daya Baran from KAUST, and Professor Kenjiro Fukuda from RIKEN. We also have Dr. Peter Zala from the Host Center serving on our panel today. So I believe their experts' perspectives are sure to enlighten us on how organic electronics are paving the way for future scientific and technological advancements in both biosensing and energy applications. So please allow me to introduce our first speaker today, Professor Dion Khodagholy. So Dion is an associate professor in the Department of Electrical Engineering at Columbia University. He received his master's degree from the University of Birmingham, and that was followed by a second master's degree and a PhD degree in microelectronics at the École de Mines in France. Before joining Columbia, he completed a postdoctoral fellowship in systems neuroscience at New York University. So he is quite well known for developing the first organic transistor in recording neural activity together with Professor George Malyaras, and then leading recent innovations in the novel device structure, including the ion-gated OECTs and the VIGTs. So his research aims to use unique properties of materials to design and develop novel electronics that allow efficient interaction with biological substrates. And the ultimate goal is to translate such advances in electronics, materials, and neuroscience into more effective diagnostics and treatments for neuropsychiatric diseases. So without further ado, let's invite Professor Khodagholy to the stage. So Dion, the screen is yours now.
Thank you very much for that very kind introduction. Let me share my screen. Is everything okay? Can you see it clearly?
Yes, looks perfect.
Excellent. Hello, everyone. I'd like to thank Professor Xu for that kind introduction and allowing me to speak today and present you some of our recent work regarding neural interface devices and their potential clinical applicability for translational devices. Generally speaking, neural interface devices fall under the umbrella of bioelectronics, a field that involves developing electronics capable of establishing coupling with biological tissue. Perhaps the humble glucose sensor would be the most well-known bioelectronic device that improves quality of life of about 30% of human beings, eliminating the need of constant daily lab visit. Of course, more advanced implantable devices such as insulin pump, pacemakers, cochlear implants can assist visceral and sensory organs to further, restore their function. Now, bioelectronics to interface with the nervous system, neuroelectronics, improve healthcare delivery and patient quality of life, while also accelerating the pace of scientific discoveries. These devices often take the form of prosthetics or electrodes that can be inserted inside the brain and record specific brain regions for the purpose of diagnosing and delivering electrical stimulation to suppress the ongoing neurological symptom. Sometimes they can take the form of full closed-loop systems where a processor acquires, processes, detects the event, and then selectively and responsively stimulates essentially the affected area. As a result, there is tremendous amount of opportunities for such devices to improve patient quality of care and, of course, advance the scientific discovery pace. Now, let me give you a tangible example of how these neural devices and neural processes operate. I'd like to focus more on learning and memory. It is known that the essentially formation of stable memories that are accessible to conscious mind go through a process that is called two-stage memory consolidation. In the first stage, during online state, the wakefulness, The information is routed to hippocampus, a highly plastic brain region that these information are encoded in form of a spike firing rate and gathered in this highly plastic and essentially synaptically interconnected regions. During second stage, offline sleep, interestingly, during sleep, these information are reactivated and broadcast from hippocampus to neocortex, a long-term memory storage unit. And often this broadcast is done through coupling of different oscillatory patterns. And as a result, we are able to consolidate short-term memories that were in hippocampus and upload them to neocortex. Now, this is a very abstract, essentially, description of how the memory consolidation happens. In practice, this is how it looks like. If you were to record electrophysiological activity from cortex and hippocampus, cortex marked with CTX and hippocampus from HC, this is how it looks like. The yellow highlighted areas are hippocampal ripples. These are fast oscillatory patterns that are known to organize individual action potential of neurons in hippocampus. And then you can see that oftentimes these yellow ripples coincide with down states and highlighted in red and blue cortical spindles. And this temporal coupling between these hippocampal and cortical oscillations allows information to be transferred from hippocampus to neocortex. In other words, this coupling, oscillatory coupling, synchronizes those two regions and allows information to be transferred. Importantly, the strength of coupling between these two regions is dynamic and contains a variety of informations. Using conformable large-scale neural interface devices shown here on the left, we basically develop a device that can cover majority of dorsal surface of the rat's cortical surface and recorded a variety of regions, including hippocampus, using an implantable device because that's in a deeper structure, and track the strength of coupling across different stages of memory and consolidation. Using essentially large data analysis methods, we were able to distinguish between consolidation versus reconsolidation processes by looking at how these couplings are associated together. In other words, we are able to decode the current state of the memory load simply by looking at oscillations. One, you can imagine it would be quite instrumental to improve memory or even suppress memory during consolidation in cases of such as traumatic experiences or PTSDs. And we're actively working in this area to turn this discovery into a more practical translational, essentially, analysis. Now, a key lesson we learned throughout this process when working with hardworking physician scientists is that in order for a device and an implant to be translatable, all aspects of it must be carefully considered. If you have a very high performance front end with thousands of channels but require high power transfer or thick interconnects, the translation of this device becomes quite limited. And based on this, I like to go and review today our approach in how to tackle different essentially challenges throughout this path. I'll start from front end, where the abiotic and biotic interface together, gradually go to pre-processing, processing of the neurophysiological signal, amplify them, filter them, how we interface with conventional essentially rigid electronics, power and data transfer, and eventually stimulation in the form of a responsive systems. Let's start. So from front end, of course, we've been always inspired by organic electronics and organic materials, specifically because of their biocompatibility, as well as the fact that they are able to conduct both ions and electrons. They are known as mixed conductors. And this is specifically important because biological processes are governed by ion transfers, not electron and holes. And so our approach here was basically by improving this interface between abiotic and biotic junction, we can potentially break this known trade-off between resolution versus invasiveness. And we wanted to be able to record more data, higher spatiotemporal essentially signals, while minimizing the invasiveness. Our approach was to combine conducting polymer electrodes with conformable electronics using bioacceptable materials such as parylene C in the form of a soft probes and surface probe. It showed that we were able to record individual action potentials from the surface of the brain in rats and without penetrating inside the brain. And because of its non-invasiveness and of course the overall biocompatibility of the device, we were able to gather all the regulatory requirements to use these devices in patients undergoing essentially epilepsy surgeries. It consists of microelectrode arrays that are coated with PSS, and there are uniform perforations along the brain. As you can see from the video, it stays nicely on the brain even when it's pulsing. There's a fluid going on. This is naturally how the brain environment is, but yet the electrodes remain nicely adhered. We were able to gather a significant amount of data with this. We had about a few hundred cells and asked the questions. Now that we have this cells and able to design our electrodes, can we come up with a data-driven design for our electrodes? So the first task we asked was, if we have a cluster of 4 electrodes known as tetrads very close to each other, what is the yield and what is the total number of cells? And this is shown in the histogram in orange. Now, if you gradually reduce the number of electrodes in a cluster, what happens to the total number of cells? As you can see, the cells drop as we go to less electrodes. However, if you notice, there's not significant drop between group of 4 and 3 electrodes. In other words, instead of using 4 electrodes, we can use 3 per cluster and use the additional electrodes that we saved, given the fact that we have constant number of essentially recording channels, and distribute them elsewhere and expand the spatial extent of our recording. And so this was nicely essentially beneficial for us because we can increase our recording area arbitrarily from surface without causing any major injury or issue, while improving the overall yield. All right, this brings us to the acquisition and processing of the data. As you can imagine, the amplifiers and the pre-processing modules such as logics and filters that interface with the system should be able to do the required electrical function, being high performance, low power, low noise, and fast devices, but also because we would like to have this amplification right at the interface, they need to be biocompatible and be sitting right next to our electrode. This makes it quite challenging because we need active devices, transistors, that can survive in vivo conditions and also be completely flexible and biocompatible. Our approach here was to essentially rely on the great work done in the area of organic electrochemical transistors, modify this, turn it into a device that can potentially serve this function. We called it internal ion-gated organic electrochemical transistors, so in short, IGTs. Now, the reason for this is that for OECTs, the electrochemical transistors, traditionally the way it operates is that the electrolyte is integral part of the device, meaning it borrows ions from electrolyte, and the intake and uptake of ions from the electrolyte causes modulation in the channel. This makes the device quite slow because it relies on the transport of ions from an external electrolyte into the channel. Additionally, because the electrolyte is shared among multiple transistors, it is challenging to individually address each transistor because electrolyte is shared among them. As a result, gating a specific transistor without a crosstalk becomes very challenging. So we hypothesized that perhaps if we were able to create a channel material that contains its own ions, we would be able to eliminate this and then introduce a gate that is electrically isolated but ionically essentially connected to this material for further doping and de-doping processes. To do this, we utilized disorbitol. This is a sugar alcohol and biocompatible material, and we blended it with PSS, and it created this water reservoirs that can embed ions from the PSS dispersion, mainly sodium ions, into the the channel material. This way, we have local ions that are at the vicinity of our P.PSS rich regions. We use chitosan, abundant polysaccharide, as our ion membrane because it has a very good ion conduction. It's processable, but also an electronic barrier to form the junction between gate electrode and our channel. So this is how the cross-section of the device looks like. And if you take an SEM image of the device, you'll see the ion membrane in red right on top of the gate, and then channel coated on top of it. These devices operate very similar to classical organic electrochemical transistors with very high transconductances. Now, the process I described to you is done with P.PSS, a P-type degenerated semiconductor, yielding to a depletion mode, normally on device. In order for electronics to operate efficiently, we also need enhancement mode, normally off devices. So, and you would like to make them be closely matched so that you can utilize them in circuitry without going through very irregular or asymmetrical design elements. So we hypothesize probably the next step to create this enhancement mode structure would be utilizing essentially a channel material that is reduced in its intrinsic state, and by application of gate voltage, we will be able to elevate its conduction. To do this, we rely on polyethylamine, PEI, to chemically reduce our P.PSS essentially channel material. And by application of negative potential, the PEI releases the bonded PSS in its intrinsic state, allowing the formation of P.PSS, hence the conductivity increases. So looking at these IV curves, the higher the gate voltage, the higher the drain current. And it was quite similar to our classical devices with very high transconductances, around tens of millisiemens, with a nice, reliable, low voltage operations. Now, interestingly, these devices, as I've mentioned, because we brought the transit time of ions to very small distances, operate very fast. In our first iteration at a few micron channel lengths, they were around a few microseconds. This was very fast, and we were very surprised by this operation, and we wanted to understand and gain mechanistic, essentially, view of what is happening here. So we made a variety of devices with different channel lengths, so the x-axis here, and then measured their time responses. The circled black dots are basically our response times of IGT, and then you can see different device transistor architecture, polysilicon or OECTs and ego FETs are put on this chart as well. The diagonal lines are the theoretical speed that can be achieved based on that given mobility. The green area is usually where essentially ion mobility resides. They're a bit slower than classical hole mobility, it's just you're moving a charged molecule. And the gray area is usually where the hole mobilities in polymer starts. Interestingly, our transistors fall under the regime where hole mobility was limiting the device. And I think what it means is that because the ions are very close to the P.PSS rich regions, the transit distance is so much reduced that now the whole mobility is the limiting factor of this process. This is a great news because a physical barrier in the device dynamics is broken, and by improving the whole mobility, we can even further improve this speed, which means we can collaborate with our chemists and material scientists to further improve our device performances. Overall, for an effective, essentially neural interface pre-processing unit, you both need speed and amplification. And these IGTs essentially play very favorably in this end because they can modulate device and the small neurophysiological signal with their high transconductances while maintaining a high speed. In fact, it allowed us to record the entire physiological spectrum from EMG, muscle activity, heart, ECG, all the way to local field potential as well as individual action potentials. There are also a lot easier to microfabricate, allowing them to quickly transform shapes and be integrated in a variety of device forms. Here we fabricated an implantable probe with several transistors that can be inserted using an anchoring hole, and we recorded individual action potentials from a rat hippocampus triggered average, as well as their quality was sufficient to cluster them and call them putative single units. But of course, these are transistors. We want to do cool operations, real-time processing with them, not only acquisition. And being able to have both depletion and enhancement mode devices allowed us to create a conformable nonlinear rectifier, where it's able to essentially rectify nonlinearly the ongoing physiological activity and amplify our interested events, which in this case are interictal epileptic form discharges. These are epileptic activity happens between seizures and are the key source of memory deficits in patients undergoing this essentially neurological disorder. Here you can see the output of our nonlinear circuit. It nicely amplifies those IEDs that are marked here and reduces the ongoing essentially baseline noise. In fact, the performance of the detection here surpasses traditional thresholding, even digital signal processing methods such as filtering and rectification. And we're now using this function directly to create a software model for our effective detections. Now, of course, show must go on. We need to push the transistor further, being able to make them denser to create more complex circuitry. Now, to do this, we obviously need to reduce the channel length to make it faster, but also come up with the methods to densely pack these together. We rely on two essentially design elements here to be able to achieve this. The first one was utilization of a vertical transistor channel. This is because majority of our conducting polymers are solution processable. We're able to stack the source and drain together, eliminate the need of complex and slow processes of ion beam lithography, and create channels that are vertical. Now, we also were able to completely encapsulate the device, but provide hydration through a vertical access point. We call it H-wire, hydration wire, where it allows water to hydrate channel and mobilize its self-sufficient ions. This is how the cross-section looks like. And the bottom is the actual device. You can see the source and drain right before the position of P.PSS on this tilt SCM. And the gate area surrounds the channel. These operated as we expected, low voltages, high transconductances, and finally broke the barrier of 1 megahertz. We went into a nanosecond regime, and the transistors are able to operate at speeds beyond megahertz, which was very exciting for us. And in fact, the combination of their gain and transconductances shown as with an analogy of transconductance normalized by channel width and their time constancies plays very favorably. It suppresses our previous work and even comparable or even better to foundry fabricated devices such as indium gallium zinc oxide or even silicon technologies. Of course, these are flexible foundry made. We were able to make dense arrays of these, in fact, 155,000 transistors per centimeter square, pack them and owing to the hydration wire, would establish a minimum crosstalk between them and place them in a area where it basically comes very close and even better to what an IGZO, essentially foundry line, can produce. This is done all in the lab. We're hoping to gradually transfer this technology and make it commercially available. But of course, another important element of the transistor is its stability over time. And I think because of the fact that this time the channel is mechanically separated from the environment and hydration is provided by H-wire, this makes the devices particularly stable. In fact, the device was able to operate continuously close to 1 year. Here we couldn't continue further, not that the device broke, we simply gave up from recording this, and I suspect we can even continue further. We made a variety of integrated devices, multi-stage amplifiers with very high gain, oscillators to create clocks and circuitry, as well as switches for multiplexing. These were all, in their terms of performances, close or comparable to what neurophysiological signals we needed, and we're hoping to gradually replace our rigid parts with this and turn into a fully conformable implant. Now, this was the pre-processing. Of course, now that we process, we need to transmit the data forward. And in order to do this, we need some sort of a communication message. Traditionally, this is done by cables and wires. But as you can imagine, this is quite a challenging one because of its biocompatibility. Also, dangers associated with having essentially hanging wires from the body and chance of infection. RF technology, specifically wireless communication, is very established in this domain, but there's a fundamental limit to this, and it's the fact that you can't implant the RF electronics deep inside the body because body is full of ions. They're ionically conducting. Majority of this radio waves gets reflected because of this conduction. Additionally, our RF circuitry are all made out of rigid and high power or consuming electronics that makes it quite challenging to be implanted. So here our approach was to utilize what body has itself and provides us naturally, and which is essentially this highly conducting medium, and develop a communication approach that utilizes ions, hence ionic communication. This is how it operates. If you have a pair of recordings that we call a transmitter, and it can be implanted inside the body. You then have another pair, RX receiver, that can sit on the surface of the skin to gather the data. We can provide a differential sweep of different frequency from the transmitter and monitor this sweep in a differential fashion from the receiver to see what is the frequency response of our cutaneous tissue. The right graph shows essentially the frequency response in a normal physiological ion concentration in the tissue, and you can see it has an inverted U shape with a fairly nice stable region on top around a few megahertz. If you change the ion concentration lower, you can see this U curve moves to the left, and if you use something less polar, let's say IP, or completely deionize the material, let's say deion water, this gain completely diminishes. So based on this change in the response of the material, we hypothesize that there are two essentially mechanisms going. On the low frequencies, this is governed by electric double layer, where ions can move back and forth, and essentially the electrodes with the water and ions interface forms this capacitors, and this is a series RC. We are very familiar with it in all electrochemical processes. At higher frequencies, when ions cannot move back and forth and they can stay stationary and vibrate, the water molecules between them becomes the dielectric constant, forming a parallel RC. And the combination of this series and parallel RC circuits creates a bandpass filter as a function of the ion concentration, yielding to this inverted U shape. This result was corroborated by our impedance spectroscopy at higher frequencies as well, and showed similar responses. So we use this physical essentially observation, transformed into a device system using digital communication, and validated what speeds we can operate. And in fact, the speeds and the data rates provided by the ionic communication is sufficient for majority of our clinical devices, as well as very advanced, high density multi-channel neural implants. Additionally, they are very low power because we're conducting across a very efficient ionic medium. The amount of power you would need for such processes is significantly less than RF or mechanical waves such as ultrasound. As a result, the efficiency of the communication defined by essentially bit per second over the wattage is very, very high. We moved on, created an implantable devices that can operate and transmit data using ionic communication. We implant them chronically in rats for essentially up to several weeks. We recorded daily, and you can see that we were able to capture neurophysiological data and transmit them outside quite reliably without any detriment in the quality of the signal down to individual action potentials from neurons that were clustered. And in fact, the clustering and the data essentially quality was high enough that you could even analyze the waveform of individual action potential, cluster them whether they're inhibitory or principal cells. So we have our data as well, but we're still missing the power. It's still traditional implants not only need data transfer, but also they need a power source. They can be transient. Let's say you have a coil or systems like that, but again they're fairly large. Or you can have an onboard battery for continuous monitoring or so. This makes the implant quite large. While possible, because of this bulkiness, it limits essentially the population of patients that can benefit from such implants. And by shrinking this down or limiting essentially the volume of the implant, we would potentially be able to provide such translational devices to more vulnerable population as well. So we thought, now that we have high performance transistors, we also have a method to transfer data using ionic communication. Perhaps we can combine these two together and create a standalone implant that can gather power externally, process and transmit data completely wirelessly back with fully conformable structure. So this is how a traditional device looks like. Let's say the neural implant is at the bottom. There's a conformable ribbon that mechanically decouples the rigid section, where it's like a potted and epoxy here. There's a power supply, the battery, and the transmitter cycles here. We thought instead of using this, we can make everything with our vertical ion-gated transistors, where a transistor is capturing neurophysiological data. Instead of having a constant voltage on its source and drain, the power can be transmitted using this ion communication. So it's actually VDS will be an alternating current, but its output, the IDS, will be modulated according to its gate's input, which is the physiological signal, and fit back using a third electrode as a data transmitter. We check whether this is feasible, how much currents we can transmit using our ionic communication. It turns out that at a millimeter scale electrodes, we're able to provide sufficient amount of current for operation of our transistors, and the performance of the transistor remained unchanged while we were comparing to DC, VDS, or alternating one. We created a fully conformable device that is only made out of essentially polymeric transistors, laminated our contacts on the skull, implanted essentially the electrodes on the surface of the brain, and monitored the neurophysiological activity over a course of days, and of course compared it to classical silicon-based amplifiers, and the performance remained essentially very similar, very stable. And this is very promising. We're hoping that we're able to essentially utilize this method in a variety of other translational devices as well. Okay, so I hope I convinced you there's a lot of opportunities for organic material and conformable electronics in translational devices and medical devices, from all the way front end with its conformable electrodes all the way down to transmission and power using transistors and ionic communication. Of course, here I'm just presenting. All of this work was done with by my wonderful lab members, and of course our hardworking collaborators and physician scientists. And funding agencies to make our work a reality. Thank you for your time. I'm happy to answer your questions.
Well, thank you so much, Dion, for this highly impressive and very inspiring talk. So I believe there are a lot of questions from the audience, yet we will leave the discussion after all the talks. Okay, so next, it is my great pleasure to introduce you Professor Daya Baran from KAUST. So Daya is an associate professor in material science and engineering at KAUST, originally from Turkey. She is a passionate scientist who received her doctorate degree from Friedrich Alexander Erlangen-Nuremberg University in material science and engineering in 2014. Her research group, Omega Lab, at KAUST focuses on engineering organic and hybrid materials for energy harvesting devices, and Daya co-authored more than 100 publications, including Nature Materials Reviews, Science, etc., and also received Helmholtz Association postdoc grant in 2015. So she's well known for pioneering work on using non-fullerene acceptors in organic photovoltaics. She was also selected for MIT Technology Review's 2018 list of 35 innovators under 35 for her development of transparent power glass that can generate electricity and block heat for greenhouses and future buildings. Besides, she is also the co-founder of 2 startups. So as a scientist and entrepreneur, she is indeed a role model to younger generations. So without further ado, let's invite Professor Baran to the stage. So Daya, the screen is yours now, please.
Thank you very much for the very kind introduction, and it's interesting to listen to yourself sometimes. I hope you can see my screen.
Yes, it's working. Yeah, perfect.
Perfect, yes. I would like to thank the organizers once again for having me here today and counting us as still young. I would like to share, let me see, sorry, give me a second. I would like to share my perspectives on the organic semiconductors from more materials side of things, adding to what Dion mentioned for the energy applications and in printed electronics today. Yeah, I would like to start with the motivation on energy, and I'm hoping whoever listening that we don't need additional in that sense to motivate ourselves that we need energy, and we need a lot of energy in several different forms. However, we need them affordable and clean, and to make them ready for the sustainable cities and the future. So in that respect, I summarized a couple of the United Nations Sustainable Development Goals to reach out to not certain communities, but to worldwide clean and affordable energy. So we are doing or working towards this in our labs, combining them with the easy and sort of more facile techniques that can be also economically feasible for future and when they're scaled up. That's why I really like printing in our labs, and we are working for different type of dimensions and for different purposes, including the energy and also soft electronics and 3D sensing. However, today I focus my talk on the energy side of things for the time's sake. And we do use printing, as I mentioned earlier, because also printing is very interesting in terms of its less energy intense production methods. I know industry is heavily relying on silicon and inorganic semiconductors, which are some of them even rare earth materials. And with the synthetic materials that you can open up a new avenue on printing using continuous coating, and we can achieve the unusual form factors and get the flexibility and conformable devices that some of them already mentioned by Dion. You have seen the electrodes that they made in the brain, that they can be conformable and also can be made via printing, for instance. And also, if we combine not only the energy need, but also the powering need for future, printing obviously opens up huge avenues for smart labeling, packaging, wearables, and also biosensing, as I mentioned. And the question comes to those as well, rather than big energy plants, how do we even power these on-demand devices and conformable electronics, which is possible with organic semiconductors. So I will make a quick dive in from this moment on to the organic photovoltaics, that you can use these organic semiconductors that can be printed and make conformable devices in the form of photovoltaics in order to generate electricity from the sunlight. So then the simplest form that you actually have a photoactive layer in this organic photovoltaic device, which is so-called a bulk heterojunction, and it combines a donor and acceptor molecule. And you create a sandwich structured device, and when the sunlight hits, or any artificial light, which can be used for indoors as well, hits to this bulk heterojunction, you create an excitone pair, and then actually the holes and electrons are separated through these interlayers to generate some electrical power. And they're very interesting because with organic photovoltaics, you can achieve semi-transparent devices, which I will share later on, and and make them ultra flexible and ultra lightweight, which I guess the next talk will touch base on that as well. And very interestingly, lately, you can use them in the integrated conformable electronics, as I mentioned. And these are all avenues we are spending our activities on. So I want to start with my PhD journey. I assume students are listening us, and how higher education and the PhD forward is quite important and would change your future. As when I started my PhD in 2010, at the time, to give you the context, in these donor acceptor systems in organic photovoltaics, the field was heavily dominated by the donor materials. And as you see, they're synthetically slightly complex materials, but very exciting polymers. Then when you change even a single atom on the peripheral groups or in the core group, you are able to change the optoelectronic properties of these materials. On the other hand, the acceptor molecule has been a soluble version of a fullerene buckyball, which is called PC60BM, over the last 20 years. So this was actually a very strong N-type material that was going very well with its donor molecules, and it has really high electron mobility and uptake electron capacity. So for all those years, the question was then, what is the ideal donor for this fullerene PCBM material? And there have been several studies to understand that in terms of design and device, etc. When I, however, finished my PhD, we started to think on maybe we should take a step back and think if we could even alternate fullerene, because there were obvious drawbacks and limitations. And one of them being is in the limited energetic levels. If you look to different PCBM derivatives, even though you functionalize them for tailored purposes, we were not really able to achieve different energetic levels, which is quite important for the photovoltaic performances. And the other one being very importantly that PCBM had a very weak visible absorption in the spectrum. Obviously, in order to make a very high performing solar cell, what you would like is that you have a huge absorption in the visible, or even preferably infrared, which was not even the question at the time, because materials designed were absorbing until 800 nanometers. However, once I moved on to my postdoc, something magical happened at the time in the field of organic photovoltaics, and I've been fortunate enough to be in there, I would say. So the electron acceptor, donor and acceptor type, or ADA type molecules have been synthesized, and we were able to make solar cells from these materials using different donor materials as well. And from that moment onwards, as you see, which was the power conversion efficiency limit for a single junction solar cell, which was about 11 to 12%, said today now is over 19% in the lab scale. There's obviously a long way to go forward. However, this has been an incremental, this has been not an incremental achievement in such a short time. And in fact, these materials not only impacted just organic photovoltaics, but also perovskite field that you might find some pseudo tandem solar cells where there's a perovskite layer were also combined with an organic photovoltaic layer. So in my labs, we have taken the approach to use an additional third component to boost the performance and also the stability of these materials. And I would like to just tell you a couple of stories. So I told you the bulk heterojunction here, the photoactive layer, consists of a donor and acceptor. And one way to boost your performance is to use adding a third component. And depending on the property of this third component, for instance, if you have an energetic landscape, ladder type energies, then you can boost the voltage. Or if you have complementary photon absorption, obviously you can increase the current in this case. Or if you design it carefully that you can have a more crystalline or orderly organized molecule, you could also fill the traps or the light-induced traps in this case and have a trap-free system boosting your fill factor. And in theory, if you can achieve all these three, you can have the all photovoltaic parameters improved in this case. Of course, saying this is sort of easy to explain. However, finding such a third component is quite tedious. And in literature at the time, the ternary approach was utilized with using two donors and an acceptor molecule, which has been fluorine in the case. And one of the breakthrough studies that we have performed back in time was using a non-fluorine acceptor as a third component in order to create this desired morphology along with energetic landscape. So this was very important here, adding this IDF-BR molecule, which was in this case, sorry, my screen, I can't hide this, relatively more amorphous compared to the IDT-BR molecule. We were able to achieve this three-phase morphology to have the optimal solar cell performance. And at the time, 7.5% was the best P3HD photovoltaic device available. And it's very important to achieve this with P3HD because P3HD was a kilogram scale material that can be actually scaled up. And nowadays, I think these acceptors also can be scaled in kilogram scale relatively easily. Yeah. So then we designed another third component because we wanted to boost the performance, obviously, and see where we can get to with the material design and from scientific perspective. In this case, we managed to combine this complementary absorption and the desired energetic landscape and even the morphological perspective with the third component, which is BITF in this case. So BIT proposes like relatively complementary absorption, and this is just normalized absorption that you need to look to the absorption coefficient and the morphology, as I said, where you can increase the pi-pi stacking when you add this third component. However, what was very interesting was that we didn't really have a ladder type energy landscape from the both perspective, but the HOMO level of this donor molecule was much lower than the PTB70H, which was another donor. So we wanted to understand how the working mechanism in terms of energetics here working. So one thing we have observed was an energy transfer that is happening from BIT to the PTB70H. This was mainly because the BIT is a wider bandgap material, and the emission from this BIT was actually absorbed by this PTB70H molecule, which was quite interesting because that was telling us that we could, in fact, provide more exciton hole pair to this donor molecule, which can then separate at this interface and increase the performance. However, there was another fact that which facilitates further performance is a hole transfer, if a hole transfer would occur from this. And for this reason, we constructed a single carrier type device and looked if there's a diode behavior or not. If you look to this inset curve here, you see that an charge transfer was contributing from the BI to the PTB70H molecule layer in this case. So these two findings actually made us think that if you would like to design an efficient ternary device, in this case, our performance was 14%, you need to combine all these parameters along with energetics and the energy and morphology, but also an energy transfer, additional to the charge transfer, was the key step to achieve the best performances. And in fact, if you're familiar with the field and look to the recent papers, now it's a common fact that the first mechanism that is happening in the donor acceptor now is an energy transfer from the donor and to the acceptor molecule, followed by a holdback and a charge transfer mechanism. This was very, very interesting back in time. So we are still continuing to looking into the ternary combinations, which is already quite complicated to understand, and you need model systems sometimes to understand also what is happening in terms of these issues. So in the second part of the talk, I would like to move now to the whole big picture. I said in the beginning how we can use actually printing and also scalability of these materials. So one of our recent work came published into publication this year, which was using the green solvents from the renewable feedstocks for not only specific to organic photovoltaics, but also to the organic electronics community. So for the printed electronics, if we look from the specific OPV perspective, this has been published a couple of years ago, showing how the translation to the higher technology readiness and to the commercialization can happen. And I just want to have your focus to the very interesting fact that the green processing is at the end of this upscaling, which I completely disagree. In considering all the health and safety, as I said, sustainability efforts that we're chasing, I would say, green processing should be, in fact, the beginning of all these efforts. However, how the scale-up of this organic electronics have been done from thousands of researchers is using glove box spin coating methods in small areas, okay, and using solar cells and evaporated, which is sort of all fine until this level, but from halogenated solvents. And I never understand why we're doing this. And our question was like, can we change this picture and look for the really green solvents? But if you look to the literature, the facts are very interesting. As I said, it's very, very difficult to find the non-aromatic solvents, which are also showing very good performances. So ideally, you would like to move away from the halogenated aromatics to the non-halogenated aromatics, which are okay, but still not enough. And you can find these materials have been published in literature. However, if you want to move to non-halogenated, non-aromatic, or even ketones, esters, and then you are much more limited. So what we did was collect and gather data for all sort of organic electronic devices, and also put it in our library in the group website. You can access here and look for if you're interested in different applications. So from the sustainable electronics perspective and the renewable feedstock, we managed to calculate some of them and gather data for the global warming potential of these simple, tiny solvents that we think we're using, but they all rely on the solvent if we're thinking printing methods. So the chloroform, for instance, most of the, even some of the OECTs are made and done from, has quite high global warming potential and the CO2 equivalent compared to the other materials. So silenes, as you see, are somehow used in the scale up of some of the OPV materials, but you're still on the positive end. And if you're thinking, as I said, the CO2 volarization, if we could find the plant-based or even somehow algae-based materials, then you can contribute to the negative concept. And how we can do it is sort of quite simple. We use the Hansen solubility parameter platform to look into dispersive polar and hydrogen forces of the solvent and look into the interaction with the solid, which is our polymers or small molecules in this case. And by using this, you can actually create a solubility sphere to a material combination and understand that if your solvent will be soluble, which if this is inside the sphere, or insoluble if it's outside of the sphere. And this is had been an intensive work published in this paper, and you can read more, which is open access as well. We have looked into several different terpene family solvents in this case that are used or produced from distillation, which are quite low in CO2 equivalent, and also modeled that if we can obtain these things from the biorefineries and the algae productions, you can even have a negative CO2 equivalent in the production of these materials. And when we made devices and optimized all the way through the photovoltaic performances, we were showing on-par performances compared to the chloroform and diiodo-octane high boiling point additives. So this was quite impressive, and I said we have shown this that it works also in transistors, LEDs, and even OECT devices. So to move on though, towards sustainability and scale up, even though you make these materials from cleaner solvents like xylene or, as I said, the terpene family, there is one further issue now relying here is the whole transport layer. If you're producing the inverted layer architectures using the zinc oxide, most of the research is still evaporating molybdenum oxide, which is a bottleneck, and it is not really thermally stable, which I will show you in some of the outdoor stability data. If you would like to heat these devices, most of the people would know that you have shunts and migration of the silver to the active layer over the time. So for this purpose, we actually moved from all the lab type production to the fab type production using the slot die coating in order to look for solution processable whole transport layers. And to do this, again, we are using the solid liquid interactions and the soluble spheres, because most of the photoactive layers that we're using from donor acceptors are hydrophobic, unfortunately, and almost all the whole transport layers that we're trying to put on top are hydrophilic, simply because we're trying to have orthogonal solvents that they don't dissolve each other. However, we want that they have very good interaction so that you don't have delamination, which I will show you in a minute. So we need to ensure this wetting and no compromise on the performance. So to understand that, what kind of material I can put on top of my photoactive layer, you can look to the wetting behavior of your photoactive layer and create such a wetting curve, so to say, using this polar and dispersive forces. And whatever is outside of your wetting curve will be the non-wetting, as you see here. And if you have formulations that would be put inside, this would be wetting. And also with this, you can understand the vertical phase separation, which is quite critical when you make devices. Again, if you're familiar with the field, you would know that accumulation of the polymer molecules on the top, which would cause you S shapes and lower fill factors. So to understand this, we have used in PTB7TH and IEICO4F system, we created a wetting curve and look into potential whole transport layers. And as you see, most of the common PDOT derivatives that are using ethylene glycol and all other derivatives are outside of this curve, which are not possible anyways. And when you look to the inside, you can, in fact, develop some of the materials combinations. However, you would end up with mechanical cracks and suffer from low conductivity when you want to make devices, which are an issue. So we developed our own ink in this case using the molybdenum oxide and PDOT combination, and achieved mechanically stable whole transport layers that are printable, and also they were retaining their conductivities over a wide range of temperatures, which was quite important, as I mentioned earlier. So out of that, I'll take you to the journey, actually long journey, telling in one slide is that we printed every layer in this organic photovoltaic devices from inkjet and slot die as well, and achieved 1 square centimeter devices, which was quite important in that case. And we break that 10% barrier in the lab scale, achieving over 70% average visible transmission just for the photoactive layer, and for the whole devices around 50%, which was quite interesting. So then what this led to were also very cool in that case, because light utilization efficiency, if you are thinking for applications such as controlled environments, agriculture, or buildings, it's very important to have high light utilization efficiency with the desired average visible transmissions. And in this case, we were quite happy with our results. So we decided to sort of scale up within the lab scale still this type of devices, and you just have seen here that the module was working in the indoor light. Actually, this is a desk lamp. So all this information, along with other PV technologies, can be found in emergingpv.org. I really care about this, and I really hope that you will promote this platform as well, that this is a platform where you can put all your data and help seeing the big picture in terms of reliable and trustworthy data representation, and see where we can get to with organic photovoltaic devices. So in the last couple of minutes, I just want to touch base on the stability aspect, as I mentioned earlier, which was quite problematic with the simple molybdenum oxide. And this work was led by one of my postdocs, Jian Han, a PhD student, Han, and maybe you can be the next one. So one issue in the OPV I showed earlier, that you can get really good performances. However, when you look to the photo stability and just put them under light, the performance was not that good in the sense of performance under light. And if you're again familiar with the field, that's why acceptor series, and specifically Y6 here, has been shown like the new hero for organic photovoltaics, and quite high performances were achieved. However, the stability is quite an issue to get sorted. And one reason why this is happening is that with heat or light, when you expose this to the photoactive layer, there's a crystallization of these molecules, or demixing, simply because these molecules can move and they don't like each other. So it's important to understand, to find material systems that like each other, or find techniques that would lock your morphology along with the proper interfaces for stable solar cells. So I'll cut it short here, but we looked into a wide range of Y series acceptors and looked first their photostability at indoors, and understand the structure property relationships, that how even a single alkyl chain or an atom can impact the outdoor photostability in the future. And among these, we briefly came with this design guideline that we need to choose fluorine type and peripheral end atoms here instead of the chlorine ones, and also longer internal side chains compared to the shorter internal side chains, that there are lots of reasons behind. And if you do this and make devices, you see that here the designed molecules that has all these design guidelines with fluorinated N groups and longer internal alkyl chains, which are N3 and Y12 in this case, have much better stability compared to the other materials. And to finalize that, we wanted to look into the outdoor stability. However, it's not that straightforward to look into outdoor stability for several devices all at once. You're limited by your equipment and design software and hardware even. And one way people do, again, globally, is to use the Keithleys, which we found and thought that's quite expensive and not to the purpose even to look into such performances. And Joel from our group has designed this micro SMU that is quite enough to use it for JV curves, which we also think that is suitable for even bio applications, and it's quite handy and small. So with this, we were able to track several solar cells and made them quite cheap as well, and made it open source that is available, but we're happy to help you out with the design of these micro SMUs. So when we put all these devices, which is a knife that in our roof in Saudi Arabia, it counts, in fact, and look for the outdoor stability over months now using this Y series acceptors, we have seen that a similar trend was also possible using these N3 and Y12 materials. So all these molecular designs told us that we should stick with the fluorine end groups, and also longer internal side chains just for the Y6 or Y series materials. But if you look overall perspective, the performance of these devices are still going down, right? And there are lots of other questions to be answered and developed in this case, starting with encapsulation, obviously, and the proper interlayers. As you see, we use a different interlayer, which is not molybdenum oxide in this case, which made it way more stable, but still we need to find effective hole transport layers over the time. So I just want to end up now with how the future looks like. There are a lot to do, obviously, still, but the whole field in the organic photovoltaics for printed electronics and the IoT type devices for power generation is moving to the stable organic electronics and look for techniques that make them more stable and resilient, and also less synthetically complex and cost efficient materials. Almost all the materials I showed you today are also requiring 15, 16 steps. So if you would like to work on those concepts, so please approach me as well as sustainability in these organic electronics is quite important and a way to move forward. And last but not least is integrating these components, obviously, with transistors and biosensors are very, very important and will make all these single-use platforms that can be contributing to the whole sustainable plastic electronics in the future. So with that, I would like to thank you for your attention, and I hope I can move to my final slide. Yes. Obviously, most of this work has been done by my group members, Omega Lab, which I'm proud to represent them today here. And I just want to show that where we are as KAUST in Saudi Arabia. KAUST is a very unique graduate university for master's and PhD opportunities. So if you like under the water to explore for a night diving or like outdoors sports, but explore them in a desert environments, please feel free to approach me, and positions are available in my group. So with all that, thank you very much.
Well, thank you so much, Daya. Really, really beautiful talk and a great overview of the organic photovoltaics from the fundamentals to the very recent innovations. Thank you again. And we will leave the discussion till the end. Yeah. So finally, I'm very pleased to introduce Professor Kenjiro Fukuda from RIKEN, Japan. Yeah, so Professor Fukuda received his PhD from the Department of Applied Physics at the University of Tokyo in 2011 under the supervision of Professor Takao Someya. And from 2011 to 2015, he worked at Yamagata University as an assistant professor and then joined RIKEN, where he is currently a senior research scientist in the thin film device laboratory and emergent soft system research team at Center for Emergent Matter Science. So from 2014 to 2018, he has also been a principal researcher of the Japan Science and Technology Agency. So Dr. Fukuda has co-authored more than 100 research articles in highly prestigious journals. His research interests include organic transistors, flexible electronics, and printed electronics. So Professor Fukuda, the stage is yours now.
Okay, thank you very much, Xiaomin-san, for your nice, kind introduction. So can I see my presentation slide?
Yes, perfect.
Okay, then my name is Kenjiro Fukuda from the RIKEN, the research group. RIKEN is a national institute in Japan. So RIKEN is not a university, so we are focusing on the researches. So today I will talk about the Ultrathin, very flexible organic solar cells. So because the Derya also already gave a very good talk related to organic solar cells from the fundamentals and the recent very stable solar cell devices in the real world, the conditions. So I will focus more on the thinness, flexibility of the organic solar cells and the potential applications using our organic solar cells. Okay. So many organic researchers are focusing on their flexibility as a very important keyword. So as Dion already gave in his speech, in his talk, the wearable devices or implant in vivo devices are target devices using organic materials, organic semiconducting materials. So this picture shows one future image of our target next generation wearable applications. So very soft, very thin, very flexible organic devices are adhered onto human skin directly or human organs directly, and their devices record the vital signals continuously for long term. So this shape is the next generation wearables. But the power source is a bottleneck toward this kind of long-term operation monitoring devices. So to solve this problem, that we are focusing on very thin, ultra flexible organic solar cells using very thin polymer substrate and very thin participation layers. So here, this picture shows that our fabricated very thin ultra flexible organic solar cells. So the important key feature is thinness. So our devices have only 3 to 4 micrometers, including substrates and participation layers. So this thin property enabled very good flexibility and very lightweight properties. And as Derya also introduced, the organic devices, organic semiconductor, organic solar cells can be fabricated using printing processes. So we can fabricate the large area, very thin organic solar cells in near future. And here is showing the summary of power conversion efficiency, PCE, of rigid, flexible, and ultra-thin organic solar cells. So as the researchers developed very good active layer materials, especially recently they developed the non-fluorine acceptor materials. The organic solar cell PCE was much improved recently and reaching the 19%, approaching to the 20%, the record values. And thanks to such a development, the both flexible and ultra flexible solar cells, the performance are also improved dramatically. And recently, the improvement of PC is mainly led by the Chinese research groups. And anyway, the recent state-of-the-art PCE value for both flexible and ultra-thin organic solar cell is reaching 17%. So these values are almost similar to the rigid certified values. So the important feature of the organic solar cell is that we can use very thin substrate and very thin participation layers. So here I show the structure of organic solar cells. So from transparent electrodes to top, normally non-transparent opaque electrode, is the functional layer of the organic solar cell devices. So, and the total device thickness from the transparent electrodes and the top electrodes is less than 1 micrometer. So if we use the 1 micron thick or several micron substrate and similar thick participation layers, we can make the several micron the organic solar cell devices. So in our group are now currently using the 1 micron thick substrate, polymer substrate, and 1 micron thick participation layers. Therefore, the total thickness is only 3 micrometers. So this is very important to achieve a large power per weight. So here is the state-of-the-art ultra-thin organic solar cells reported by Professor Chan's group in China. And they developed the very good organic solar cells fabricated on a 1 micron thick substrate. And this solar cell is very lightweight, as shown here. And this has a very large power per weight value. The calculated value is reaching 40 watt per gram. So if we prepare the 1 gram solar cells, it can generate 40 watt. This amazing value, it can be achieved by thanks to usage of the very thin substrate and the organic semiconducting materials. So in addition to the increased power conversion efficiency, PCE, there are other important parameters. The one is the mechanical robustness. Because we are using the flexible, very thin substrate, the flexibility is very important parameter. So we try to improve both the efficiency and the mechanical robustness, such as bendability, or some cases, the stretchability is another important parameter. And the second important parameter is environmental stability. So we need to solve the instability problems against many environmental parameters such as air, oxygen, water, or thermal stabilities. So we need to solve these environmental stability issues. Even we use the very thin substrate. So these bottom figures show the progress of our very thin ultra flexible organic solar cells. So first we focused on the flexibility, and then next we focused on the waterproof properties. And the next we achieved very thermally stable organic solar cells. So that's enables the thermal processing to adhere our solar cell devices onto the textiles using the hot melt processes. So this achievement was achieved by the Xiaoming several years before. So this is very good work. So I would like to show some recent progresses of using the novel materials. So we currently are focusing on the novel materials, interface materials, and the interface itself. So in this study, we have had a collaborate with Professor Infa Cho from the HUSD Wuhan, and we developed a new electron transport layer. So the hybrid materials of the organic and metal oxide materials. So we named this hybrid material as the PI zinc. And this combined the hybrid PI zinc ETL show very good performance, stability, and mechanical robustness simultaneously. So here is the jailbreak performance of our ultra flexible organic solar cells using the PI zinc as a ETL layers. We use the state of the art, the active layer PM6Y6 as the photoactive layers, and we compare the conventional zinc oxide ETL and PI zinc ETL, and we found that PI zinc show almost same or a little bit improved PCE in comparison with the zinc oxide based conventional solar cells. And with PI zinc as ETL, we achieved 15.8% as the best PCE value. So this can secure that PI zinc can work perfectly as ETL layer for state-of-the-art organic solar cell materials. And a more important point is the much improved the mechanical robustness. We tested the many combination of the transparent electrodes and ETL materials. So when we use the ITO, very brittle, the transparent electrodes, when we apply the harsh mechanical strength to the devices, the device performance was sharply degraded even after only one cycle when we use the ITO and the zinc oxide combinations. But such a harsh degradation was suppressed dramatically when we replace the zinc oxide with Pi zinc, as shown here. So with this combination, the device can work after the around 10 cycles. And we then change the transparent electrodes from brittle ITO to more stable silver nanowires. And we also compared the mechanical robustness between zinc oxide and Pi zinc. And we found still Pi zinc show much better mechanical robustness than zinc oxide materials. And finally, we changed the silver nanowire transparent electrode to polymer PSS. Then this combination PSS as a transparent electrode, Pi zinc as the ATL show best mechanical robustness. As shown here, even after 100 harsh the mechanical strain release cycles, the PCE remains almost same. There is almost no degradation even after the 100 cycles. So this clearly showed the usage of the organic materials or hybrid materials, hybrid interfaces enable the mechanical robust the organic devices. So this is very important point for future the highly flexible organic solar cells and related organic electronic device systems. Then we are focusing on the how to integrate the such organic flexible devices onto the any curved surfaces. And this the work was achieved by our previous postdoc Stephen. He had the expertise on the mechanical engineering. So he developed a very nice approaches using the lamination process with shrinkable, thermally shrinkable films. So he combined the thermally shrinkable films and our very thin organic solar cells or organic devices, very thin organic devices. And he attached such shrink film and ultra-thin devices onto the curved surfaces like sphere, as shown here. And he applied a heating, a 130 degrees C heating to the whole systems. Then the devices automatically shrunk and conform to any complex shape of the curved surfaces, as shown here. So even after such a process, the organic solar cell worked perfectly because our organic solar cells have both good mechanical robustness and very good thermal stabilities. So here I showed some demonstration of the lamination of our solar cells onto the complex surfaces. For example, on the irregular surfaces, this is the Japanese traditional toy, Daruma, the toy. And this has the irregular surfaces. And he also adhered onto the very sharp angles and multiple radius, both the concave, convex, the shape. And even after the lamination onto such a complex surfaces, our organic solar cells work perfectly as shown here. Because the light intensity angle is slightly changed, the current is slightly decreased from the initial value to the after the laminated values. But anyway, our organic solar cells worked normally. So this can clearly show that our solar cells can be laminated onto any curved surfaces. So this is very important point for the future curved electronics applications. And we also show this proof of concept using the different electronic devices. Here, this is the very simple touch sensor devices. And we laminate this simple touch sensor devices onto any curved surfaces, such as the coffee cups, mouse, or door knobs. And even after the lamination process, these devices can work perfectly as the touch sensor devices. Okay. Then next we try to focus on how to make the integrated devices. So even though we fabricate very thin organic solar cells, very thin sensors, if there is no the technology to integrate each other, such a interconnect region lose the flexibility, their flexibility. So we developed no adhesive direct conductive bonding method. So here is the photo of the integrated systems of the organic solar cells and OLED devices. So these devices are fabricated separately on 1 micron thick substrate. And after the fabrication, we integrated these two devices by using these 1 micron thick gold electrodes films. So these integrated devices was achieved with newly developed the bonding technologies. We use the water vapor plasma treatment onto the gold surfaces. And after the treatment of the gold surfaces, we gently laminated these two gold electrodes, and we store the such laminated gold interface in ambient air for several hours. In this experiment, the massa left this film left in for 12 hours. But anyway, we didn't apply any thermal process, any additional pressures. So we just store this sample in ambient air for several hours. Then we can make the perfect bonded interfaces of the gold, these two gold surfaces. And the important the mechanism is the generated the OH regions onto the gold surfaces after the water vapor plasma treatment. And here is the cross-sectional SEM image after the bonded samples. So top here is the top gold layer, and here is the bottom gold layers. And you can see that this region, there is almost no boundaries. And you can see this region, the interface from this region or this region. But mostly such interfaces are almost disappeared. So this cross-sectional SEM image clearly shows we can make the perfect gold bonding by using such simple water vapor plasma treatment technologies. And we observe the EDX analysis of this interface region and bulk gold regions. And we observe that this interface, this white region imply the little bit increased oxygen amount. So we guess that the generated OH groups can make the hydroxyl bonding first. Then this bonding can be was converted to the metal, gold metal bonding later in ambient air conditions. And with these technologies, we achieved this kind of the integrated working systems. So when we apply this strong sunlight illumination to the OPB, all it works. So this confirms that such integrated systems are working perfectly. And even after this kind of the mechanical strain, crumpling, bending procedure, our integrated systems work perfectly. So this can show that our bonding can secure the flexibility of the full integrated devices. And this can work as a very good technology as the integration of the very thin organic electronic device systems. And by using these kind of technologies, we are now trying to increase the integration of the devices. So in this study, we integrated solar cell modules, organic LEDs, and organic photo detectors to make the wearable sensor systems. So we applied, when sunlight illumination was applied to the OPV modules, this energy operate the organic LEDs, and with this light illumination, the OPD photo detector detect the vital signals. So here is the result of our self-powered PPG sensor systems. So we succeeded in the monitoring of the blood pulse by using this kind of the Ultrathin, the self-powered PPG sensor systems. So maybe this is one good example of the future application using our very thin organic solar cells. And lastly, I would like to show you another very interesting result that may be related to the both wearable electronics and the soft robot devices. So we discussed with the Professor Sato in the Nanyang Technological University, Singapore, that he is the expert of the cyborg insect the researches. And we had a discussion, and we came up with the idea to integrate our solar cells onto the cyborg insect bodies to make the rechargeable cyborg insect devices. So here is the photograph of the actual cyborg insect that we fabricated. The very thin organic solar cells are adhered onto the insect abdominal surfaces, and the other rigid components are integrated, adhered onto the tracks of the insect bodies, as shown here. So this organic solar cell can generate the power, energy, and then supply to the batteries, and then battery is recharged with the organic solar cell energies. And then these systems can operate the cyborg insects. So the important finding through this research is that thinness is very important parameter to achieve the basic motion ability of insects. So here is the movie clip with different thick film adhered onto the insect bodies, insect abdomen. So if we use enough thin the film, the insect can do this kind of upside down, the self-lighting movement. But if the film thickness is over 10 micron, the insect cannot do this self-lighting the attempts. So this is very important because we fortunately, we fabricate 4 micron thick, 3 micron thick organic solar cells. So I show you this video again. The adhesion of such a 4 micron thick organic solar cells do not interfere the basic motion ability of this insect. So we try to evaluate with a physical analysis, and we found that we can express the self-lighting success rate by using the buckling load of the films adhered onto the abdomen. So we adhered different polymer films and different film thicknesses. So Paridene is a little bit rigid, the materials, that having the Young's modulus of around 1 gigapascal, several gigapascal. The PDMS is very soft, rubber-like rubber materials. The Young's modulus is the order of the megapascal. So then we calculated the buckling load of these different materials and different thicknesses. And we obtain these buckling load values. And we plot this writing success rate as a function of the buckling load of these two different materials. And we observed there are very good relations between the writing success rate and the buckling load. And maybe the threshold force is around 0.1 Newton. So this value is within the acceptable range of that the one insect can generate. So the important message is a quantitative description of how thinness, softness affects insect basic motion ability can be achieved. So we believe that this kind of the evaluation can be applicable for other insect species or the other soft robot devices. And anyway, the enough thinness, enough softness is very beneficial toward such a wearable devices and soft robot, mini soft robot applications. And here is the final demonstration of the integrated systems. So before charging, so we cannot control the insect locomotion at all. But we apply the sunlight to the solar cells that are adhered onto the insect bodies. And after the charging process, we succeeded the wireless motion locomotion control by using the integrated systems. So as you can see from this movie clip, so this is the summary figures. So when we push the stimulation on button, right button, the insect successfully turned right, as you can, as shown here, these right figures. And after we turn off the stimulation, the insect go straight again. So this is the demonstration of the rechargeable cyber insects devices by using Ultrathin organic solar cells. Okay, so this is the end of my talk. I would like to thank all collaborators in RIKEN Takasumi Research Group and University of Tokyo Takasumi Research Group and other collaborators in RIKEN, Hiroshima University, Waseda University, UCSB, NTU, HUST, and some other fundings. Thank you very much for your listening.
Well, thank you so much, Guo-san, for this highly inspiring and excellent talk. Also quite interesting demonstration with the insects. So now let's thank all the speakers for the excellent talk. And then please let me introduce our panelist today, Dr. Peter Zala from Host Center. So Peter obtained his PhD in chemistry from the University of California, Santa Barbara in 2014 under the supervision of Professor Quinn Nguyen. And then his doctoral research focused on the characterization of the optical and electronic properties of novel pi-conjugated polymers. He then joined the group of Professor Takao Someya at the University of Tokyo as a project researcher. During that time, he worked on developing optoelectronic devices based on organic semiconductors for electronic skins and wearable medical monitoring. And then in 2017, he joined Host Center to continue his research in printed flexible and large area electronics. He is currently leading the large area sensors and functional hybrid arrays research programs at the Host Center. So, Peter, very glad to have your thoughts on the discussions shared today, and maybe your reflections first to the three talks, please.
Okay. Well, Xiaoming, thank you very much for the kind introduction, and also thank you for organizing this. It was really nice to get in touch with the research that others are doing around the world. I knew a little bit of what Fukuda-san is busy with, but as for Professor Khodagholy and Professor Baran, I was not 100% familiar. But I found the presentations really nice to see overall. However, at least from my perspective, I'm really curious to understand from the speakers a few things that would maybe come from an industrial perspective that I come in touch with here at the Full Center. So, well, I don't know how you want to organize such a discussion, but yeah.
Maybe you can start with a few questions that you have for these talks.
For example, from the first presentation about the transistors, I was really curious to understand, for example, what kind of uniformity in terms of mobility or transconductance can be obtained for this 155,000 sensor array. And I was further from that, I was also interested to know how does such a variation affect the gathering of the signals. So if one sensor is a little bit, I don't know, worse than the other, how does that ultimately affect your spatial resolution? And yeah, as a third part to that question, I was wondering if this process is scalable to large wafers or onto a kind of flat panel display type manufacturing method.
Mm-hmm. Yeah, thank you very much for your comment and questions. So it was very important for us to be able to have a very reliable uniform gain and speed across our transistors because we were planning to make circuits and we carefully characterize that. We are using commercially available polymers, and we use analytical grade chemistry. So pH 1000 is our dispersion of heat. It's particularly consistent. So we have well below 5% variation in transconductances. And I mean, I suspect if we move towards more, advanced and experimental material, this will fluctuate. But certainly, the fluctuation will be somewhere at the level of material where we can hopefully over time control it, and it's not raised by the processes. As to the fab process itself, it is a fully lithographic process. It's slightly different in terms of orders and general arrangement of it, but it is possible to do all of this in outside foundry facilities that, given the fact that they don't do major CMOS work because you can't have ions inside and so on. And in fact, we've tried to do a few of this in a large scale roll-to-roll manufacturing close to our area. In terms of variation, that's an interesting point indeed. So to our surprise, I always, as an electrical engineer and also then moved to organic electronics, I always imagined silicon foundry will be everything down to the 0.001 precision and everything organized and there's no variation. In fact, even the CMOS fab tolerates 20% variation across. That's not little. And the main reason is we're able to make electronics so good and yet consistent, reliable is partially because the way we design the circuits. The way the arrangement of the transistors allows for this variation. What we found out is, at least for our material, it is slightly different compared to silicon ones. The closer we get and the denser we pack, the higher the consistency. Because obviously, in our case, is organic and so on. We do have issues when we scale it extremely large. So within chip, the variation is very little. But if you want to expand, say, across chip variations, that's where the numbers start going into high single digit or even 2-digit percent changes.
Okay, yeah, thank you very much. I think I understand. And following up from, let's say, conventional technology, how can you, I think for the audience, it's probably nice to give some direct comparison of your technology that you are working on versus, let's say, more old school approaches like ISFETs based either on polycrystalline silicon or on metal oxide semiconductors like IGZO. And in your opinion, if we study those platforms for recording, these old school platforms, what can we what do you think we can learn from that can help us in the organic?
Yeah. I mean, those are very interesting technologies themselves. Our main motivation of using essentially the conducting polymer or like mixed conducting polymers was the fact that they can conduct ions as well. And so at the interface, instead of having a surface or a 2D double electric layer capacitance, because the ions can penetrate inside the bulk of the material, you have this volumetric capacitance. The entire bulk of the material is engaged. As a result, its efficiency to interact with in vivo or even electrolytic processes is very, very high. And also, it doesn't need any encapsulation for survival. The silicon technology is very mature, very advanced, but because you will have a danger of ion implantation or surface oxidation, you always have to encapsulate them. And as a result, you always will end up having a 2D interface. I guess probably one can always argue, and I think that's the optimal solution when we're essentially those technologies become mature enough that we combine them together. The surface or the direct interaction will be done by polymers that are tailored for in vivo application, and then high digital signal processing will be seamlessly continued with silicon.
Cool. Yeah, I agree. I think it's very nice to consider, for example, integration of these types of transistors with IGZO backplane, for example, that would enable you to still have something flexible. I don't know how implantable it is. That's totally out of my realm, but I think it would be nice to have a really fully integrated system. Yeah, I don't know, Xiaomin, if you have anything to add, or if I should ask to another speaker, or how you would like to proceed.
Maybe you can proceed with, questions to Daya and Fukuda-san, and I will follow up after you.
Okay, sure. So then, well, to keep the order, then I wrote a few questions for Professor Baran. So, yeah, mostly I'm curious, when you do these long-term tests in the environment, you showed always kind of the power conversion efficiency evolution over time. But if you decompose this efficiency over time into other metrics like VOC or changes in fill factor, do you see, the same trend, or do you see kind of opposite trends? And from decomposition of these parameters, what could you deduce further from what's actually going on in the sample?
Yeah, thank you very much, Peter, taking the slack on asking questions to us. I appreciate it from topic to topic on that sense. It's a very valid question. In fact, we are working on outdoor stability and how to assess that, right? When you do an indoor stability, it's obviously an accelerated test. And then we sort of say T80 is the metric. However, we realize when you go for outdoors, obviously it just depends on the weather and the day and so on. So it's not really, you can tell, the performance loss if you had so many cloudy days and all of a sudden sunny day, for instance. And I think we have a lot to learn from the silicon industry in that sense. But coming back to your question, and because the trend, the PC is the multiplication of the current voltage and the fill factor, the trends are also degrading. However, the most significant ones are in the fill factor most of the time. That's why I emphasize the significance of the interlayers. Kenjiro also mentioned with the ETLs. In our case, it's mostly whole transport layer. Is that something is happening there? We looked into things like the surface recombination increases over time. We also have seen actually the silver as electrode has the penetration, unfortunately. However, thinking more industrial applications, sometimes it's working through the grid. You might have more passivating layers in between the photoactive layer and the whole transport layer. I believe some of those can be eliminated. However, we believe there's a mechanical delamination from the photoactive layer to the top layer, which is the problem and that we heavily see in the field factor in the long-term stability.
So that's some kind of mismatch of thermal expansion, or is that the origin of that delamination?
Yeah, very good question. We haven't looked to the thermal coefficients and so on, to be honest. I got the similar question before. We haven't looked into that. And I don't know what exactly, I can't say this is done, but when the light hits that specific interface from the organic layers through the whole transport layers, sometimes doesn't like each other, right? That's all I can say at this point. I mean, there are reports on sort of superoxides and they trigger further reactions within themselves and so on. But specific to our measurements, it was already a long way to be able to measure and look into the correlations. Now we are digging into sort of this question, what is happening? But definitely I can tell that there's surface recombination over time that is killing. That means it's between the photoactive layer and the whole transport layer in that case.
And finally, you mentioned that you are looking into large area solutions for fabricating of these cells, but have you also been looking into encapsulation solutions that are compatible with your process?
Yeah, thank you again. It's very industry relevant question, of course, and Kenjiro also showed some of the whole encapsulation, and it's a pain. If you realize some encapsulations that are commercially available that you work and they, for instance, require UV curing, and that is not very much aligned with your material properties, or you need to apply heat as well and so on. So then you need to find heat resistant photoactive layers that can actually tolerate that, right? So I think there's a huge gap there, basically. And that needs to be addressed. And it's not only for organics, by the way. I think perovskites community suffer from the similar issues. And yeah, we haven't done, to be honest, anything specific, but we are working with colleagues at KAUST that they work for perovskites and develop encapsulants and so on. And yeah, I think that's why it's very important material scientists and chemists should come together to new designs, and it's all reiterating, right? So I find it like you need to push the field and also take a step back afterwards, push it and take a step back. So with all this work, I think we have seen that the materials can be scaled up. To be honest, we looked to 200 square meter scaling up of these materials, which was successful. But then we need to step back to, as you said, what are the issues with encapsulation and how that can be mitigated. Yeah, totally fair.
Thank you very much. And then, yeah, finally, I would like to move to Fukuda, Professor Fukuda, to ask a few questions. And I'm always, whenever you see the demonstrations from RIKEN or the lab of Professor Someya, it's always really impressive to see those very thin devices, especially seeing that you can laminate them and on basically any shape that you want. But one question I always have is how do you, and I would like to get your perspective, how do you see handling these types of devices on a really large scale? So yeah, it's nice to see that you can delaminate these from a small glass carrier, but how do you think of, really making these, so that I can laminate really large objects in the end?
Okay, thank you very much for your good question. So I skipped such a detail in my presentation. So actually, we use the rigid glass support during the fabrication. After the fabrication, we delaminate the very thin devices from the such glass support. So then we normally we use the physical delamination processes, but I know that there are several other methods such as dissolving the sacrificing layers or laser process to delamination processes. So maybe for the large area devices, maybe we need to advance these delamination processes. So for example, I know that laser assisted delamination is the matured process for the OLED device fabrication. So advanced processes using such a laser delamination process can be applied for the future, the very thin, the organic devices. So maybe this will be the one approaches, how to handle the devices. Anyway, we first fabricate with the rigid or thicker film support. And after the fabrication, we delaminate the very thin devices from the such support.
Yeah. And yeah, thank you very much. And as the next question, maybe it's something maybe for all the speakers, because I see that I think all of you are using this so-called PEI material. And I would be curious to know, how does this PEI layer affect the environmental stability of the devices that you create, or the long-term stability?
So in our cases that we developed a new ETL, the PEI, and mixed with the zinc, the devices, and we observed that this PEI mixed structure can prevent the penetration of the zinc, the atoms or ion to the active layers during the aging process, the high thermal stress, or any other processes. So I guess the unfavorable penetration is very important. So anyway, the interface, the engineering is very important topic for the future organic source devices, as Derya mentioned. So maybe, of course, we need to improve all instability problems further. But anyway, we need to carefully coordinate, design the interface between the ETL and the active layer, or active layer and HCl, or the transport layer and electrodes.
Yeah, I can understand. And then my last question, I think in the interest of time, to you, Fukuda-san, would be, so you showed very nicely this bonding of gold to gold. That allows you to really create these devices that can be separately fabricated and then integrated with one another. But have you also explored the bonding of other metals like copper or silver? For example, I can imagine that the bonding of copper maybe to gold or copper to copper would really allow you to interface with some more conventional flex or rigid PCBs that maybe help you to make a really heterogeneously integrated system.
Okay, thank you very much for your very good question. So actually, this is the currently ongoing project. So we try to develop the bondings. So beyond the gold bonding, we try to make the bonding between the other metals and other metals. And so this is still ongoing. So it's not good timing for me to share the information, but maybe in the future we can show the result. But anyway, with the plasma assisted bonding is was well-known technology. So we modified this the surface activated bonding technology with the newly developed the water vapor plasma process. So we will focus the related technologies to further develop our direct bonding technologies, not only for gold, but also other metals or polymers or metal oxide materials. I hope that we can further expand the materials.
Cool. I think, yeah, that's very exciting maybe for all of us here, all of the presenters, yeah, for really creating more advanced systems in the future. So yeah, those are all my questions that I listed. I don't know if, yeah, Professor Shu wants to add something else, but yeah.
Yeah, great questions and perspectives. Thank you so much, Peter. And yeah, just follow the questions maybe to Daya and Fukuda-san, both of you. So have you considered like combine the energy harvesters with energy storage system? especially for Daya, the rooftop demonstration of the transparent OPV are really, really impressive, right? So have you ever sort of like storing those energies? Yeah.
Yeah, thank you. It's a very good question as well. So maybe not in the groove, but I can say that both Dion and Kenjiro showed that in the integrated circuits, where if we could ask the question, I was going to ask Dion, how do you get your power, basically, right? And then you just connect somehow electrodes, and it would be fantastic to just maybe use the light instead of any electrical power also to integrate those systems. And then in that case, you obviously need to do a certain storage or use a capacitor type element in there, which we work on it with my other colleagues on bio applications. That is definitely possible. I think the challenges there are like, how do you supply? Do you need the current or the voltage, etc., and how would you supply that and store? And in terms of the roof applications, definitely that is possible. But I also would like to say maybe not in the common sense of batteries, that you can, if you want to use them, for instance, for greenhouse applications, you can think to also convert to thermal energy and store in that sense in terms of not direct electrical energy, because those systems, if you look to greenhouses, they're quite cheap, and then the batteries are also not very cheap technologies. And then always the question comes to like, yeah, you add then you add the battery to store your system, like how that comes industrially is a challenge. I think it would be fantastic if we could just design the single device that could generate and store both of them. Would be much more interesting than, generate the electricity and store and those types of things. The short answer is like, no, we don't do that, but I think that's definitely interesting to move towards.
Yeah, cool. So Fukuda-san, what opinion?
Actually, we had the experience of the integration of our rootless flexible organic solar cell with the supercapacitor devices. So we fabricated a very thin, the total photo charging device systems. And in the insect study, we just used the lithium polymer battery as a storage devices. But for most cases, the storage devices is necessary. So in my opinion, if we aim the flexible integrated systems, battery is very challenging topic because the volume, storage volume, should be decided by the volume. So for solar cells, this can be decided by the area, but for solar cells, for batteries, the volume is very important parameter. So this means if we reduce the thickness, the storage amount is sharply decreased. So maybe we need to consider the balance between the storage amount and the consumption, energy consumption. So I think, in my opinion, the very good breakthrough is needed for the battery devices. So maybe the very large the storage capacity, the power volume, this kind of devices can improve the integrated wearable system dramatically. So I really hope to develop these kind of the battery devices, but unfortunately we don't have the enough knowledge, expertise on the battery or material science. So I hope one researcher will develop this kind of very good battery systems in future. And we really want to collaborate this such a newly developed battery system with our the very thin harvesting devices. So this will be the very good future direction.
Yeah, exactly. It's really crucial to overcome the trade-offs between the mechanical flexibility and the electrical performance of the battery systems. Indeed. Yeah, great. So I've received a couple of questions from the audience as well. So one question from the student to Daya is that So we know that compared to fullerene acceptors, the non-fullerene acceptors are regarded to have a better stability. However, some current research indicates that the thermal stability of maybe a single non-fullerene binary system can also be significantly improved when we add the fullerene components, like the PCBM, to form a ternary system, right? So besides an effective regulation of miscibility achieved by adding the PCBM as a third phase, are there any other possible reasons? Yeah. So what is your perspective toward this question?
Thank you. Very, very technical question, and yeah, to the point as well. But yeah, that's right. The whoever writes is true, but it's not because it's PCBM, right? Thermodynamically, when you add more and more materials, and in fact, we just have a recently accepted publication now in Nature Communications. You can look like we did hexagonal solar cells to just prove that concept to increase the thermal conductivity because of the data gives free energy is actually more driven to the thermally favorable situations. And so that's not just because of the fluorine. If you add another small molecule acceptor, which is NFA, that is also becoming the case. But obviously, stability is not only the consideration. You need to look like how can I maximize my performance as well. If you use a non-fullerene acceptor, then you can complement the absorption. Which is also can be the case for fullerenes because that area is not covered, and also increase the performance as well as the stability. That is true, but mainly it's driven morphologically and thermodynamically. Yeah.
All right, thank you. Yeah, and following this question, you have also a very nice review paper talking about the third additive, right? And so you have mentioned the roles played by the additive, including forming a cascade energy level diagram, extending the absorption profile to the near-infrared range, and also the ordered nanophases and trap-free charge transfer. So from your perspective, which of the role dominates? Because we are having sometimes very tiny little amount of the additive in the whole system, right? So, yeah.
That is true. That's a really, really nice question. So I used to give talks ending up saying like there will be always a better ternary than a binary solar cell. Because you can always make the binaries better with the ternary aspect. But the question would be then, why am I doing that ternary? And I always said like if the aim is that if you're binary, you should look into the problem of your binary system. For instance, if you have two materials that can be commercially viable, right? Made in kilogram scales, they're extremely cheap. However, they have a voltage problem. And then I think you could design a third component and the voltage would be your bottleneck in that case. Or you have two systems and then they're terribly stable. I think then the third component could come into play to solve that issue. So I'm not going to say like one over the other, but I showed that there's obviously now the efficiency, cost, and stability triangle, which people talk now. I add the sustainability in it. You need to look into what solutions we would like to bring. That is more important than people try to push the efficiency all the time. It's not the case. I think having a large area, over 15%, and stable device is a good enough to get into market for certain issues, even 10%, to be honest. I know that there are a couple of startups and companies like Epishine working towards them and they're not even that performance. So it's to touch to those points equally rather than trying to push one to the sky in that respect. And that's why we need to look into the problems we have and what we would like to solve, I would say.
Yeah, thank you so much for your insights. And to Fukuda-san, so what is your current goal? Like, what is the next step for the ultra-flexible organic solar cells?
Oh, this is very good question. And maybe as Peter asked to Derya, the stability is very important issue for the flexible organic solar cell because if we reduce the thickness of the substrate and the passivation layer, the gas barrier property is sharply degraded. So under such conditions, we need to improve the operational stability. So we need to consider the combined stability issues, light illumination, thermal issues, and the existence of the water, gas, oxygen penetration to the devices. So the related to the Peter's comment, we need to develop the passivation layers having the enough good properties to secure the device stability. So maybe this should be very important point, but there should be the trade-off between the good barrier properties and the good flexibilities, because if we make the soft barrier layers, this means the barrier property should be degraded. So we need to try to find the good way to achieve the enough flexibility and enough good the operational stability simultaneously. So this should be very important direction for us.
Yeah, thanks a lot. So as Peter mentioned, there is a common material called PEI involved in all the talks. As I noticed, there's also another material, P.PSS, right? So this is especially important for Dion's work, as this is a very classic and prototype mixed conductors of the ionic and electronic. So, Dion, are you still considering other material candidates instead of P.PSS, or what is your view on that?
Yeah, of course, we're always looking for new materials. Our next step in essentially developing materials for bioelectronics would be those that allow us to complementary circuitry. And so being able to have either electron conductors, N-types, or utilizing essentially this mixed conduction to not only interact with cations, but also anions, because remember, this is both an ion and electron circuit, so you can very well utilize negative ions instead of your electron conductors to make this complementary circuit. So we have a few candidates. We're working. I'm not a material synthesis person. We're working very closely with researchers in Purdue and MIT to establish this process, and it's an ongoing work for sure. I think that will be the next front. And of course, the classical essentially roadmaps of material development, their higher ion mobility, more biocompatible solvents, more going away from all the bad things that and solvents that Daya eloquently explained would be a major advantage as well.
Yeah, thank you. And there are a few questions from the students. So, for instance, the student is very curious about the edge veer that you presented in the VIGT work, the edge veer. So he's wondering, what's the scale of this edge veer, and if this can provide the VIGT channel with water to hydrate the whole channel, then does it mean that these circuits can only work in the environment full of water? How about in a non-hydrated environment? Yeah, so this is a question from the student.
Excellent question. Yes, so the scale of the idea behind HVIA is create a water conduit to hydrate the channel. Now, the scale of this should be such that it causes a significantly large electrochemical impedance from the channel to the outside world. As such, will be a nice barrier and eliminating crosstalk. We have our HYIs down in the scale of a few micron, usually 2 by 2 or 5 by 5 micrometer, while the channel width is larger than this. As a result, we have a big impedance mismatch. The reason that basically majority of the applications we're going to use these devices are in electrolytic environment. There will be some sort of electrolyte and water presence. and in the body, outside body as a sensor. So there's always hydration around. We've also prepared a version of this that we were able to pre-hydrate the channel and then contact it with electrode. That's very well feasible as well. But the student is absolutely right that the water is critical for operation of these devices because we want to make sure the ions can be mobilized and move freely. Whether it's coming from HYA or you preload it, both are possibilities.
Yes, thanks a lot. And the last question. So in your VIGT work, actually, we see combined advantages. For instance, the very fast response, the low voltage input, the very high level of integration and absence of crosstalk, and eventually the demonstration of a standalone system. So everything seems so perfect. Are there still flaws or remaining challenges to be tackled? Yeah.
Yes, that's nice of you, but there's a long way to go. It is true that we're moving forward to having the better transistor, but there's a long way from one transistor to actually making a system. Multi-channel, essentially neural interface device would be obviously a next logical step. We've only demonstrated them one. Being able to stimulate is another critical factor that we should consider. There's a variety of elements that one should be integrated. And of course, as I mentioned, this was done on a depletion or an enhancement mode device. We should be able to make this such that they become complementary and have all the four quadrants under control.
Yeah, great insights. Thank you so much. So time is quite limited. I guess with that, it's good time to wrap up. So our speakers today have not only presented very profound, insights into the fundamental physics of electronic and optoelectronics, but also shed light on their pivotal applications across multiple disciplines. So I believe their insights will help us see the significant potential that future implementation of organic electronics holds. So finally, please present the certificates on behalf of RIKEN to our speakers today. So this is to Dion, Khodagholy, to Professor Daya, Baran, and finally to Professor Kenjiro Fukuda. And Alice will also send you the e-certificate through the email box very soon. And thank you all again for joining us tonight. And last but not least, a heartfelt thanks to everyone for your active engagement today. So RIKEN Youth Talks look forward to, welcoming you every Tuesday evening. So for more enlightening discussions. So next we will focus on the topic of advanced materials and sensing technology. Really look forward to that. So until next time, goodbye and take care, everyone. Thank you.
Thank you very much for your invitation.
Thank you.
不再是奇迹，不再是幻想，此刻真感觉全世界对我鼓掌。不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞。不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。I can。没有什么可以阻挡心中无限的力量。I can 我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can，没有什么可以阻挡心中无限的力量。I can，你也能够像我一样飞越最高山岗。I can，没有什么可以阻挡心中无限的力量。I can，你也能够像我一样飞越最